In the last class, we had discussed some of the problems related to moment of inertia. We shall now move on to the next set of problems that is related to plane rotation. Okay. Now, we had already studied that in case of a planar motion, the equations for the kinetics of rigid bodies are given as mx equals minus ixz into omega dot plus Iyz into omega square. My equals minus Iyz omega dot plus Ixz into omega square, and mz is equal to Izz into omega dot. So these were the equations which we had studied in case of a planar motion for a arbitrary reference frame. Okay, I'll just write it here. In which the body is undergoing rotation only in the xy plane. Okay. Now, in case, if you consider a special case, okay, in which the axis of rotation, okay, the axis of rotation coincides with the z-axis of the reference frame. Okay, so the axis of rotation coincides with the z-axis of the reference frame. Okay, in that case, mx and my will be equal to 0. Mx and my is equal to 0 as such, because Ixz, similarly Iyz will all be equal to 0. So what remains is that you have only one equation. You have only one equation, and that equation it is mz equals Izz into omega dot, or we can say it as Izz into alpha. So this is the equation which we use in case of a pure rotation, okay, and the rotation is in such a way that it coincides with the z-axis. The axis of rotation coincides with the z-axis of the reference frame. So this is the equation which we shall be using in majority of the problems related to the planar rotation. Okay, so let's go to the first question. A stepped cylinder has the dimensions r1 equals 0.3 meter, r2 equals 0.65 meter, and the radius of gyration k equals 0.35 meter. The mass of the stepped cylinder is 100 kilograms. Weights A and B are connected to the cylinder. If the weight B is of mass 90 kg and weight A is of the mass 50 kg, how far does A move in 5 seconds? In which direction does it move? Two stepped cylinders are attached to a point here, so they are undergoing a pure rotation. Okay, you have two sets of weights, weight A and B, that is attached to the stepped cylinder through strings here as shown in this figure. The corresponding mass of both these weights are given. It is asked to find the distance traveled by the body A after 5 seconds and the direction in which it will travel. So first we shall write the data that is given to us. Okay, we have the mass of body A that is given as 50 kilograms, the mass of body B that is given as 80 kilograms. Okay, Then the radius of gyration k is given as 0.35, and the radius of the stepped cylinders, okay, one radius r, capital R1 is given as 0.3 meters and R2 is given as 0.65 meters. Now, in order to solve this question, we first find the acceleration of the bodies B as well as A. Okay, we find the acceleration of the bodies B as well as A, and then we relate it to the rotation of this corresponding stepped cylinder. Okay, so first let me draw the free body diagram of both of these corresponding blocks. So you have here the block B, okay, you have the tension in the cable, let's say TA, and you have the weight acting downwards. The mass of the body, this is body A here. The mass of this body, it is 50 kilograms, so the weight will be 50 g. And then you have a body B here, okay, it has got a tension in the rope TB as well as the weight, since it is mass is 80 kilograms, the weight will be 80 g. If you look at these bodies here, one of these bodies will go up while the other will come down. Okay, one of these bodies will go up while the other will come down. Since the body B is having more weight, so as such I assume that this body B is moving downwards. Okay, so as such the body A will move upwards. If you look at this stepped cylinder, you can see that when this body B moves downwards, the cylinder here will undergo anti-clockwise motion. Okay, both these are connected. Both these outer and inner cylinders are connected. So as such, body A will move upwards. For the time being, as such, I will consider that body A is moving upwards with an acceleration, say AA, and at the same time body B is moving downwards with an acceleration AB. Okay, so applying Newton's law, sigma Fy equals m into Ay. So that will give me, for body A it will be dA minus 50g is equal to 50 into the acceleration of A. For body B, since it is moving in the downward direction, okay, so 80g minus dB is equal to 80 into AB. So these are the two equations we had obtained right now. Okay, now you see here the stepped cylinder is undergoing an anti-clockwise rotation with respect to this corresponding point. Let the angular acceleration of this stepped cylinder be alpha. Okay, so the stepped cylinder rotating in anti-clockwise direction, then angular acceleration alpha. Okay, now if it rotates with an angular acceleration alpha here, let me show you in this figure. You see this corresponding at this edge, there will be an acceleration downwards. Okay, and there will be at this corresponding point acceleration upwards. So this acceleration downwards is equal to the acceleration of this body. So this I can write it as AB, and this I can write it as AA. Okay, now if you are given the corresponding radius of the cylinder, we can easily relate the acceleration. So this corresponding AB and AA are actually the tangential acceleration when this cylinder is rotating here. Okay, so as such I can write AA as, you see here AA will be R2 into alpha. Okay, R2 into alpha. As such I am concentrating on the magnitude only. Okay, so here AA will be equal to R2 into alpha, that is equal to 0.65 into alpha, and AB will be equal to R1 into alpha, that is 0.3 into alpha. So you can see here that this acceleration AA is the tangential acceleration of this stepped cylinder, or the outer one, and this acceleration AB is the tangential acceleration of the inner cylinder. Okay, now substituting these values in this equation, you would get TA will be equal to, okay, 50 into 0.65 alpha plus 50 G. Okay, so that would give me 32.5 plus 490.5, and TB as such would be 80 G minus 80 into AB, that is 0.3 alpha. So as such, if you substitute, I would get 784.8 minus 24 alpha. So here we have obtained TA and TB in terms of, sorry, you have here alpha here. Okay, TA and TB in terms of the angular acceleration alpha. Now we apply the equation m equals I into alpha, where m here it is the moment or torque with respect to the center of the rotation here. So in this figure, if you see here, okay, so you have this corresponding body A at a distance of R1 and this corresponding body B at a distance of R2. Okay, so as such, if I take moment, you see the external force acting in this case is only the weight here. The external force acting in this case is only the weight here. So if I take the moment of this corresponding value, so let me draw the free body diagram here once again. You have the inner cylinder and the outer cylinder. Okay, so as such you have TB acting here as well as TA acting here. Okay, now if I take moments with respect to the center of the point, center of the cylinder, okay, so M will be equal to TB into 0.3. This will be in anti-clockwise direction, so as such I will take it as positive. Then minus TA into 0.65. This is in clockwise direction, so as such I have taken the negative sign, is equal to I. Now I as such, you have been given the mass as well as the radius of gyration. So as such M will be the total mass 100 multiplied by this radius of gyration square into alpha. Now substituting TB and TA from the equations we had obtained earlier, 784.8 minus 24 alpha into 0.3 minus 32.5 into alpha plus 490.5 multiplied by 0.65. This is equal to 100 into 0.3 whole square into alpha. So if you solve this equation, you would get 40.575 alpha is equal to minus 83.385, or alpha is equal to minus 2.055 radians per second square. So as such, we had obtained alpha is equal to minus 2.055. That means the corresponding body is undergoing a clockwise rotation. So since we obtained a negative value here, that means the entire stepped cylinder is undergoing a clockwise. Now substituting this corresponding alpha equals minus 2.055 in the equation we had obtained earlier. Okay, so as such, A of A is equal to, now we are concerned with only the motion of body A, as in the question only that is asked. So AA will be equal to 0.65 alpha, that is equal to 0.65 into minus 2.055, which will be equal to minus 1.336 meter per second square. Okay, so as such, the velocity at A will be equal to minus 1.336 t plus c1. We are integrating acceleration to obtain the velocity. Now at time t equals 0, okay, initially when the corresponding step cylinder is started from rest, so at that point v is equal to, or velocity of A is equal to 0. So as such, if you substitute this, you would get c1 equals 0. That means VA is equal to minus 1.336 into T. So if you integrate it again, you would get the vertical distance traveled by A will be equal to 1.336 T square by 2 plus C2. Okay, now again at time T equals 0, okay, the distance traveled by the body A will be 0. That indicates C2 is also equal to 0. Therefore, YA will be equal to 1.336 by 2. So there is a negative sign here. Okay, YA is equal to minus 0.668 T square. Okay, so at time T equals 5 seconds, okay, YA will be equal to minus 0.668 into 5 square, which would give me minus 16.7 meters. So as such, this indicates that the body A will drop a distance of 16.7 meters after 5 seconds. So this is what is asked in the question. Now moving on to the next question. The body shown in figure consists of a homogeneous slender bar 1 that is rigidly connected to the homogeneous sphere 2. The body is rotating in the vertical plane about the pin at O. When the position is in the position, that is when theta is equal to 30 degree, its angular velocity is omega equals 1.2 radians per second clockwise. At this instant, determine the angular acceleration alpha and the magnitude of the pin reaction at O. This question is from the textbook by Andrew Python. So you see, you have a bar here, and then a sphere that is attached to the end of the bar. Okay, the mass of the bar as well as the sphere is given. The radius of the sphere is given to you. Omega 1.2 radians per second is given to you, and the L value is given to you. Now the question is to find the corresponding reactions at point O at this instant when theta equals 30 degrees. Now in the earlier section when we had studied kinetics of particles, we had solved a similar type of problem, okay, in which there will not be any mass for this slender rod. Okay, this corresponding rod will have a negligible mass, and there will only be this sphere which I assume it to be a particle. But in this case, the rod as well as the sphere has mass. So as such, we will have to use the kinetics of rigid bodies while solving this type of problem. So first we shall just look into the basic equation that for rotation, pure rotation, that is m equals I into alpha. So here we'll have to find m is the moment of the corresponding rigid body about the point. So here, since the rotation is with respect to this point O, I'll have to find the moment of the forces with respect to this point O. Similarly, I'll have to find the mass moment of inertia of this rigid body with respect to the point O. Let me first look into the moment. For that case, you will need to draw the free body diagram of this corresponding rigid body. So here you have slender bar here, and then you have the sphere here. Okay, so as such, you have the weight of this slender bar acting vertically downwards. The mass of it is 30, so as such you have a weight 30 g. Similarly, at this center of the sphere, you will have a weight due to the sphere here, that would be 80 g, since the corresponding weight of this corresponding mass of this sphere is given to you as 80. And then you have the pin joint here, so as such you will have got reactions here. For the time being, let me express the reactions in terms of the normal and tangential coordinates. I will tell you why a bit later. So you have here, say, F N as well as F T here. Okay, so Fn are the Fn and Ft are the corresponding reactions. Okay, Fn and Ft are the normal and tangential reactions at point O. Okay, so the moment, since the body is undergoing rotation with respect to this point O here, okay, I'll just draw it here. So as such, the moment of the entire rigid body with respect to this point O will be equal to, you see, you have here this corresponding weight acting vertically downwards. It will be in the clockwise direction here. So this will be equal to minus 30 g into, now the distance is given to you as 800 mm. So as such, this distance will be equal to 0.4 meters. Similarly, the distance to the center of the sphere is given to you as 1 meter. So minus 30 g into, now the horizontal distance of this corresponding force is from this point A. Okay, this distance, it will be 0.4 cos 30. Similarly, this distance will be 0.8 1 cos 30. So as such, minus 30g into 0.4 cos 30 minus 80g into 1 cos 30. I told you I had taken minus sign here. Why? Because it is undergoing a clockwise moment. So as such, I had taken negative here. So if you solve this, okay, you would get minus 781.61 Newton meter. Now next is to find the mass moment of inertia of this corresponding body with respect to the point O here. Now I hope you remember the concepts of mass moment of inertia which we had discussed in the last class, and we had solved some of the problems related to it. Now so this corresponding rigid body has two parts, a rod here as well as a sphere here. So as such, the mass moment of inertia should be taken as sum of both of these with respect to an axis that is perpendicular to the plane of this paper. Okay, with respect to an axis that is perpendicular to the plane of this paper, and then it should be shifted or expressed in terms of the point O. This can be done by using the parallel axis theorem. Okay, so remember one thing in mind, I am finding the moment of inertia with respect to an axis that is perpendicular to this plane of this screen here. Okay, so as such, I will be equal to, now first I shall look into the sphere. Now for a sphere, you know that we have studied that the mass moment of inertia with respect to an axis that is passing through the center of the sphere is given as 2 by 5 into mr square. Okay, 2 by 5 into mr square. Let me call it as now plus m into the distance. Okay, the distance between this corresponding center of the sphere and this point. I'll call it square. Okay, plus now the second thing is regarding the rod. You know that the corresponding equation of a rod with respect to the center is ml square by 12. Or you must have also studied the mass moment of inertia with respect to an axis that is at one end of the rod. It is ml square by 3. So I can directly apply that corresponding equation ml square by 3. But if you are feeling it confused, you can start from the basics. Okay, so I'll start from basics. M L square divided by 12 plus M D square. Okay, so this will be equal to 2 by 5 into 80 into that r square is the corresponding radius of the sphere. So that is given as 0.2. So 0.2 square plus m180 into the distance of the sphere, center of the sphere from this point, it is 1 meter. So 1 square plus m2 30. The length of the rod, it is 0.8 meters. So 0.8 square divided by 12 plus 30 into the corresponding distance of this axis from which we are finding it. Okay, so that is 0.4. So 0.4 square. So if you solve this, you would get 81.28 plus 6.4, that is equal to 87.68 kilogram meter square. Okay, so substituting both of these in this corresponding equation here, you would get minus 781.61 is equal to 87.68 into alpha, or alpha is equal to minus 8.914 radians per second square. Okay. Now here we had found out the angular acceleration of the entire rigid body with respect to the point O here. Now next we have to find the magnitude of the reactions at the point O here. The magnitude of the reactions. To understand that concept properly, let me draw the mass acceleration diagram. Okay, so you have already drawn the free body diagram here. Okay, this is the free body diagram. Okay, now we'll draw the mass acceleration diagram, sometimes referred to as MAD. Okay, so here you have slender rod here. You have the sphere here. Okay, now since we are finding the rotation of this entire rigid body by assuming that this entire slender rod is having the weight that is concentrated at the center point of this, and the sphere is having its weight concentrated at the center point of the sphere here. Okay, so as such we will draw the corresponding acceleration components of these centers here. Okay, so you have here, okay, the tangential component of the rod as well as the normal component of the rod. Similarly, you have here the tangential component of the sphere here as well as the normal component of the sphere here. Okay, so as such when I apply the Newton's laws, okay, this is the Newton's laws. For that, before the apply Newton's laws, I'll find the corresponding values of these normal and tangential components. Now an of r, okay, the normal component of the acceleration of the rod here, this will be equal to r1 into omega 1 square. Okay, so since it is undergoing pure rotation with respect to the point O here, so this will be equal to 0.4 into 1.2 square, that is equal to 0.576, okay, meter per second square. Now I am looking only at the magnitude here. Okay, I am looking only at the magnitude. Then you have the tangential component of the rod here, which will be equal to r1 into alpha. Now alpha is the angular acceleration, so 0.4 into 8.914. As I told you, I am looking only at the magnitude. Okay, I know this is undergoing, here minus indicates that it is undergoing a clockwise rotation. So this will be equal to 3.566 meter per second square. Now the normal component of the sphere, okay, this will be equal to the same equation. Okay, as such the value of r changes, so r will be equal to 1 into 1.2 square. Here 1 is the distance from of the center of the sphere from this point O here. Okay, this is 1 meter. Okay, not the radius of the sphere. Okay, so this will be equal to 1.44 meter per second square, and then you have the tangential component of the sphere here, that will be equal to the corresponding distance from the center multiplied by 8.914. This will be equal to 8.914 meter per second square. Okay, so now we had obtained the acceleration components of the center of the rod here as well as the center of the sphere here based on the rotation with respect to the point O here. Okay. Now we'll relate the forces and the acceleration components. So first, applying the Newton's law along the normal direction. Applying Newton's law, sigma Fn is equal to m into An. Okay, now let's look at the free body diagram here. Okay, you have the corresponding force Fn that is acting along the normal direction, and then for the time being I'll write this Fno and Fto, distinguish between the force acting at point O. Now you have this force here acting along the normal direction, as well as this 30 G's vertically downwards. So as such, you will have a component of force that is acting along the normal direction here. Similarly, you will have a component that is acting along the normal direction. Both will be the sine component. So this will be equal to Fno, the force at point O, plus 30 G sine theta plus 80 G sine theta. So these three are the forces that is acting along the normal direction. And then we have to look into the mass into acceleration components along the normal direction. So here you have the normal component of acceleration of the rod as well as the normal component of acceleration of the sphere here. So this will be equal to m. So the mass of the rod will be 30 into the corresponding An component, it is 0.576. Now since this is towards the left, I'll put a negative sign here. Okay, and again you have this negative sign 80 into the corresponding value 1.44. Okay, 1.44. So if you solve this, you would get Fno is equal to theta. Here it is, as you know, it is 30 degree. So if you solve this, you will get Fno, the normal component of the force acting on the pin will be equal to minus 672.03 Newton. Similarly, you can apply the corresponding Newton's law along the tangential direction. Okay, so along the tangential direction here you have FTO that is acting perpendicular to this rod here, and the component of 30G that is parallel to this. Okay, that will be 30G cos theta, and the component of 80G that is parallel to this, that will be 80G cos theta. So as such, F of TO that is in this direction and the other two will be in this direction. So as such, minus 30G cos theta minus 80G cos theta. Now this will be equal to, you see, the corresponding tangential components of the acceleration of the rod as well as the sphere. Since this is downward direction, I'll put the negative sign. Okay, that is equal to minus corresponding mass of the rod 30 into the acceleration, tangential acceleration of the rod, that is 3.566, minus the mass of the sphere 80 and the tangential acceleration of the sphere 8.914. Okay, so if you substitute here, G is 9.81, theta is 30 degrees. So if you substitute here, the tangential component of force at the pin will be equal to 114.42 Newton. Therefore, the reaction at pin O will be equal to root of 672.03 square plus 114.42 square. So this will be equal to 681.70 Newton. So here we had found out the reaction at point O by applying the Newton's laws. Okay, So you'll need to understand the concept properly for applying the Newton's law. You'll have to use, in some cases, the mass acceleration diagram, okay, depending upon the question. Now let's go to the next question. A shaft A is rotating at an angular speed of 1750 rpm when the handbrake is applied. If the shaft and its part have a radius of gyration of 200 mm and a mass of 500 kilograms, how long does it take to halve the speed of shaft? The dynamic coefficient of friction between the belt and the shaft, it is 0.3. Okay, so in this question you have been given a braking system, okay, that is being controlled by a handbrake here. Okay, a force 300 Newton acts at this corresponding point here. So what happens is that there is a belt here that runs throughout like this. Okay, there is a belt here that runs throughout around the cylinder here. So when this is pushed towards right, this belt gets tightened, which will force the shaft to reduce its rotation. Okay, so as such, in the question it is given that the shaft is initially rotating with a angular speed of 1750 rpm. So omega 0 is equal to 1750 rpm. Okay, so which will be equal to, if you convert it to radians per second, 1750 into 2 pi by 60. Okay, so this would give me 183.26 radians per second. Okay, and the mass of the shaft is given to you as 500 kg. Okay, the radius is given as 0.2 meters, and then the coefficient of dynamic friction is given as 0.3. The radius of gyration is given as 0.2 meters. The radius, it is 0.3 here, not 0.2. Okay. Now first, how do you solve problems related to this? Okay, we'll have to draw the free body diagram. Okay, so that here you can apply the corresponding equation m equals I alpha for this question. In order to apply this m equals I alpha here, you will need to know the forces in these ropes here at this end as well as at this end. So for that, we'll have to draw the free body diagram of this corresponding brake here. So let me draw the free body diagram of both of these, and then we'll proceed with our solution. Okay, so as such, you have the disc here, and then I'll draw it separately. You have the shaft here. Okay, so 300 Newton at the topmost end. You see, at this corresponding point here, there is a hinge here, so you'll have maybe normal reactions at this point. Okay, and then this corresponding belt here, okay, it will say as such it has a force, say T1. Okay, and there is also a belt at this end, that is, so this would be T2. Okay. Now if I take this corresponding disc here, okay, the rope here as such will have a tension T1 here, and the rope at this end will have a tension T2 upward here, opposite to this one. Now first we shall consider the free body diagram of the shaft here. Now our aim is to get a relationship between T1, T2 and this 300 Newton. So as such, if you take moments about a point here, Okay, maybe this point, and then these two forces will be not come into picture. For the time being, I'll name it as point A. This will be, say, for example, point O. Okay, so sigma MA is equal to, now you see, break here, I can apply sigma MA equals 0 for this corresponding shaft here. So as such, so the force here T1, the distance are given to you already. This is 0.3 meters and this is 0.2 meters. Okay. So F1 into 0.2. This will be in the anti-clockwise direction, so that will be positive. Okay. Plus F2 into this distance is also 0.2, so that is also in the clockwise direction, and plus 300 into this distance will be 0.5. This is clockwise, so I'll write it as negative. That is equal to 0. So if you solve this, you would get F1 plus F2 is equal to 750 Newton. So this is the first equation which we get. Okay, now I'll take the free body diagram of the disk. You see, in this disk here, you have a corresponding belt that rolls over this. Now in this disk here, you see you have the tension in the cable here T1 and the tension in the cable here T2. So since friction is involved here, T1 and T2 will not be equal. Okay, so you must have studied the relationship in case of a rope or a cable that is wound over a disc or a pulley system which has friction. The equation we had studied is that T1 by T2 is equal to E raised to mu theta. We had already studied this equation earlier and we had solved a problem also. So T1 is the tensile force in, say, at this end, and T2 is the tensile force at the other end. In this corresponding equation, T1 will always be greater than T2, or the equation should be written in such a way that the numerator should be greater than the denominator. So in this figure here, if you see here, you see this is being pulled by the 300 Newton force. So as such, the corresponding tension in this cable will be much greater compared to that in this cable, since this is wound over this one. So as such, T1 here will be greater than T2. That is why I had used the equation in this format, where theta as such represents the angle, okay, the angle over which the cable or the rope is wound over. Now, to substituting the value, E raised to mu, as you know, it is 0.3, and theta, you see, this corresponding cable here wounds over this circle, okay, for an angle equal to this angle, okay, for an angle that is equal to this corresponding angle. So since the total angle is 2 pi, I can say it is 3/4 of 2 pi, okay, 3/4 of 2 pi. So from this I would get T1 is equal to 4.11 T2. Okay, T1 equals 4.11 T2. So this is also, I'll write it. This is T1. So T1, T2, T1, T2. Okay. Now substituting this equation, you would get T1 equals 603.26 Newton and T2 equals 146.74 Newton. So here we had found out the corresponding tension in the cables T1 and T2. Now, once you know this corresponding value of T1 and T2, we can apply the equation M equals I into alpha for, since this corresponding disk is rotating with respect to this point O here. M is equal to I into alpha. Okay, you can write I omega dot or I theta double dot, both are the same thing. Okay, now M as such, you see, you are finding the moment of this corresponding forces with respect to the center here. So the radius is 0.3, so T1 into 0.3, that will be clockwise, and T2 into 0.3, that will be anti-clockwise. So anti-clockwise will be positive, clockwise will be negative. So as such, T1 it is give you, T1 will yield you a clockwise moment. So I'll write minus 603.26 into 0.3, and T2 will give you an anti-clockwise moment. So plus 146.74 into 0.3. Now I here, you see the mass as well as the radius of gyration is given to you. So I will be equal to M into K square. So M, it is 500 kilograms into K square 0.2 square, okay, into alpha. So if you solve this, you will get alpha is equal to minus 6.848 radians per second square. Okay. Now, besides finding the angular velocity, the question is to find how long. Okay, how long does it take to halve the speed of the shaft? That is a question. So now, if you integrate it, we will get omega. So minus 6.848 into T plus C1. Now it is given that at time T equals 0, omega 0, it is given as 183.26. Okay, so substituting in this corresponding equation, you will get C1 is equal to 183.26. Therefore, omega will be equal to minus 6.848 T plus 183.26. So our question is to find the time required to reduce the angular velocity by half of the initial value. So it will be equal to by half of 183.26 by 2. That would be equal to 91.63. So substituting this value in this equation here, 91.63 is equal to minus 6.848 T plus 183.26. So if you solve this, you will get time equals 13.38 seconds. So this is the time required to reduce the corresponding angular velocity of the disk here to half the angular velocity initial. Half the initial angular velocity. Now moving on to the next question. A torque T of 15 Newton meter is applied to a rod AB as shown. At B, there is a pin which slides in a frictionless slot in a disc E, whose mass is 10 kilograms and whose radius of gyration is 300 mm. If the system is at rest at the instant shown, what is the angular acceleration of the rod and the disc? The rod has a mass of 18 kilograms. Now here you have a rod here which has a torque T here in the clockwise direction. So as such, it will undergo a clockwise rotation, and this disc here and this rod here is in a slot within this disc here, which is also pinned to a point here. So this disc also undergoes anti-clockwise motion. Now the question is to find the angular acceleration of both the rod as well as that of the disc here. So here in the question, you have been given the mass of the rod here that is 18 kilograms. You have been given the mass of the disc here, it is 10 kilograms, and then you have been given the length of the rod here, that is 0.8 meters, and then the radius of gyration k of the disc here, k2, it is given as 0.3 meter, and finally the moment or torque, it is given as 15 Newton meter. Okay. Now both the torque and the moment are the same thing. Okay, you can use either capital M or capital T to indicate the torque or moment. Now, so first, how do we solve this problem? We first draw the free body diagram of both of these bodies. Okay, the rod is having a mass of 18 kilograms, so as such its weight will be 18 g. Okay, now as such there will be reaction forces at both of these points. Okay, for the time being I call this as Fx and Fy, and then you see at this corresponding end here, this is in contact with this disc here, so there will be a reaction at this end. Okay, there will be a reaction at this end, so that reaction, the disc offers a reaction that is towards the right on this corresponding rod here. Okay, so as such you will have a reaction here. Okay, I'll just call it as, since this point B here, I'll call it as FB. There will only be horizontal reaction, there will not be any vertical reaction since it can slide in the vertical direction. Okay, so from the free body diagram of the rod here, now here one thing you have to remember is that both these bodies are separate. Both these bodies are separate bodies. Okay, so as such the angular acceleration of this rod here will be different compared to the angular acceleration of this disc here. Okay, so as such you will have to use the equation m equals I into alpha separately for these two bodies. So for the rod you have m1 is equal to, now here m1 is capital M. Okay, don't get confused between capital M and small m. Small m is the mass, so m1 is equal to I1 into alpha 1. Now in this corresponding rod there is also a torque here which I had failed to express it here. There is a torque here, that is 15 Newton meter. Now I take the moments with respect to, say, the point O here. Okay, so as such I'll have, now 15 is in the clockwise direction, so it will become minus 15, and then 18g, that will also cause a clockwise moment, so minus 18g into the corresponding perpendicular distance between point O and 18g. You see it is given that the corresponding angle is 30 degree here, so this is here 30 degree. So as such the length of this, which you already know, it is 0.8 meters. So as such this will become half 0.4 into cos 30. Okay, and then FB here will have a anti-clockwise moment, so it will be positive, so plus FB into 0.8 sine 30. Okay, this corresponding distance, vertical distance, will be 0.8 sine 30. Okay, so this will be equal to, now the corresponding, the mass moment of inertia of this rod with respect to this point here. Now you had already studied that the moment of inertia with respect to an axis that is perpendicular to the screen here and passing through the center of the rod. You must also study the equation in case it is perpendicular to the screen and passing through one of the edge. Okay, or you can use the parallel axis theorem to shift this here. For the time being, I'm using it directly. Okay, if it is at the center, it is ml square by 12. If it is at one of the ends, it is ml square by 3. Okay, so as such, I will be using this corresponding equation directly. So mass into 18 into L square 0.8 square divided by 3 into alpha 1. Okay, so if you solve this, you will get minus 76.17 plus 0.4 FB is equal to 3.83 into alpha 1. This is your first equation. Now coming to the free body diagram of the disk here. Now you have the disk here, which is having a slot somewhere here. Now at a particular instant of time, when this corresponding rod is at 30 degree, you see there is a reaction FB here, so that reaction I'll reverse it. Okay, it will be FB in this direction. Now in the question, it is given the distance at that particular instant. It is 0.4 from the center. So if this is the center O here, okay, this will be 0.4 meters. So here also we apply the equation M2 is equal to I2 into alpha 2. Alpha 1 is separate, alpha 2 is separate. Okay, now moment of the force, that is about this center of rotation here, there is only one force here. So this will be, since it is in anti-clockwise direction, it will be positive. So FB into 0.4 is equal to I2, this corresponding the mass moment of inertia of this disk. Now the radius of gyration of this disk is given here, so I can directly write mass, that is 10 kilograms into the square of the radius of gyration, that is 0.3 square into alpha 2. Okay, so 0.4 FB is equal to 0.9 into alpha 2. So you have got two equations here. One thing which I would like to say is that, see, both of these corresponding bodies are undergoing rotation and they are linked. Okay, they are linked. So I can say that the acceleration of this point here, B point, okay, when I take the rotation of this corresponding rod here with respect to this point O here, it will have an acceleration AR here. Tangential acceleration, since it is rotating with respect to this point here. Now the horizontal component of this acceleration at this corresponding point, it will be called as AD here. Okay, this corresponding ATB, its horizontal component is what which drives this corresponding disk to move here. Okay, so kinematics, okay, I can say that the horizontal acceleration at point B is same for the rod as well as the disk. Okay, the acceleration of the disk at point B, okay, will be equal to AR into sine 30. Okay, you have here this angle 30 degree here, so this is AR. So this horizontal component towards the left will be AR sine 30. Okay, so AD equals AR sine 30. Now AD is towards the right and AR is towards the left. 0.4 into alpha 2. Since the disk is undergoing an anti-clockwise rotation, I'll keep alpha 2 as it is, but AR as such but the rod is undergoing a clockwise movement. So as such, the angular acceleration of the rod I'll keep as negative. So AR it is 0.8 into minus alpha 1 into sine 30. Okay. So if you solve this, you will get alpha 2 equals minus alpha 1. Okay. The disk is undergoing an anti-clockwise rotation, so it is positive. The rod is undergoing a clockwise rotation, so as such I given minus alpha 1. Now substituting in the equation, okay, you have this equation here, so you get 0.4 FB is equal to minus 0.9 alpha 1. Equation 2 here, okay, and then substituting this in equation 1 here, okay, you have minus 76.17 minus 76.17 plus 0.4 FB, but you have obtained 0.4 FB as minus 0.9 alpha 1. So minus 0.9 alpha 1 is equal to this is 3.83 alpha 1. Okay, so 3.83 alpha 1, from which I'll get alpha 1 is equal to 16.10 radians per second square. Okay. So in the question, it is required to find the angular acceleration of the rod as well as of the disk. So the angular acceleration of the rod is 16.10, of the disk it will be minus 16.10 radians per second square. Okay. So with this we come to the end of the problems related to pure rotation. From the next class we shall deal with the problems related to general motion, which includes both rotation as well as translation. Thank you all.